Welcome to the EOL seminar. After a little break over the winter holidays, we are back. And it is my pleasure to introduce today's speaker, Professor GyuWon Lee. And he's a professor at the Department of Astronomy and Atmospheric Sciences of the Pyeongchang National University in South Korea. So Professor Lee received his master's degree from Pyeongchang National University and his PhD from McGill in Canada. After his graduation, he actually spent some time here in NCAR, and he was also a research associate at the Marshall Radar Observatory in Canada. And he is an expert in radar meteorology, and I see many radar experts here, which is good. And he's also an expert in cloud physics and precipitation forecasting. And he served as an editor of the Asia-Pacific Journal of Atmospheric Sciences. And he's a lead scientist from the Korean Academy of Sciences. And he also received the Presidential Award for his service to the meteorological community. And with that, let's get started with Professor Lee's presentation on IcePop.
Thank you. Thank you. I'm glad to be here to give a seminar. So I appreciate all the participants for the seminar. And also I know couple of people actually participating through the webcast. So they couldn't come down from CSU here. So today I will talk about what we are doing with the IcePop 2018. So it was an international collaborative experiment for Pyeongchang Olympic and Paralympic 2018 Winter Games. So this was a WMO RDP FDP program. And I would like to thank you to my student and postdoc, and in particular KD An from KMA. So this experiment wasn't happen without the tremendous help from the KMA. And also the many international participants, so NASA, Walt Peterson, UCLM, Francisco Tapiador, Alexis Brun, and Bani Notoros from CSU. So let me start with the scientific issue in terms of mechanism. So this is satellite image, actually. So when we have a cold air outbreak, there is some interaction between cold air with warm sea. So there is heat and moisture transfer. And also when northeasterly flow comes in this way, actually flow goes all the way to the coastal area, and then immediately they start to meet the topography. So between the coastal line to the mountain range is about 10 to 15 kilometers, pretty close. So there is an orographic lift as well as a convergence between land and ocean. And also whenever it lifted, then there is a sort of a complex flow actually generated by the topography. So that make very complex microphysical processes as well as dynamical processes. So these types of storm we call the east snowstorm actually has very low predictability in enthalpy model. And also one of the issues with these types of system is very few observation over the ocean. And also this involves LC interaction as well as scale transition from synoptic to mesoscale, even microscale. And also due to the change of the land and ocean, the surface, so you have so much complexity in the precipitation phase as well as the microphysics driven by the dynamical flow. And also, a lot of people was looking into the NWP scientific issue in terms of NWP prediction. And they want to develop seamless prediction from the nowcasting to the short-range forecasting by combining all existing the predictions system. And also, they want to test predictability over the NWP over mountainous and complex terrain. So basically, they want to have sort of very detailed information from the IOP observation to compare with the NWP performance. As well as I was interested in microphysics, so we want to do some systematic evaluation of a different microphysical scheme, and in particular for the winter precipitation. So then that will lead to some improvement or some new development of microphysical parameterization in NWP model. So when we started this observation, so we had some limitation in observational systems, since we are talking about the mountain range, complex terrain. So as I explained before, here this is coastal line, and then this is cross-section along that line. So you see immediately you have topography, terrain, mountain about 1 to 1.5 kilometer height. It's not that high, but the distance between ocean to the coastal line, the mountain range is very short. So the slope is pretty steep. So one of the issues in this area, before we started experiment, we had only one operational sounding in this location. This one single sounding actually covered entire area. So we are actually basically lack of sounding information. So we want to, first ultimate goal was we want to add, we want to get the high resolution and high temporal and spatial resolution sounding, as well as we want to have a very high resolution wind measurement at upstream and downstream. And also in terms of remote sensing, we are talking about the ocean and talking about the mountainous area. So basically we are lack of observation at lower level. So we want to add some the remote sensing capability to get the three-dimensional wind as well as low-level radar observation. And also one of the missing components was cloud observation, even for the clear air too. And then in terms of microphysics, so we are very much focused on the microphysical parameterization. We try to set up the supersite to observe detailed microphysics at the ground. So we set up the supersite along the flow as well as cross flow too. And also we had some instrumentation to measure snow particle or snow habit at the ground too. So in terms of supersite, we call this is the supersite along the barrier. So when the northeasterly flow comes in, this will be the line before they cross the mountain range. So we set up the several digitometer as well as the surface station. And then the next one is we call the supersite along the flow. So when the flow comes in, this will give you actually eventually the Lagrangian change of a precipitation system. So how when the flow comes in, how the precipitation actually modulates by topography. So we set up all different instruments along this line. So this includes, we want to see the very detailed structure, vertical structure of precipitation, as well as ground microphysics. And also we want to have the snow water equivalent too. So this is sort of an list of instruments along those flow. So from the coast, mountaintop, and the valley area. So each site has equipped with we call the micro rain radar that can give you the vertical structure, and also perceivable and pulse digitometer. So that will give you the surface microphysics, as well as fluvio. It's a rain gauge that gives you the snow water equivalent. So those are all equipped with we call the windshield. And also we have two major sites in the mountaintop as well as valley area. So this was existing cloud physics observation site. So that has a lot of different microphysical as well as aerosol information too. And then this one, major supersite MHS, was we built from scratch actually. So we set up the so-called DFIR, double fence intercomparison reference, and that's basically we wanna host different instruments that can be protected from wind. So in that way we can eliminate the wind effect. So within this instrument we set up the perceivable and 2DVD and mask and fluvio too. So this is upper air sounding observation. we had two window profiler, one in upstream and the other is downstream, so in the valley area. And then beside that, we have about 4 additional sounding stations, and also as well as there is a mobile sounding station too, so car 1 and 2 and 3. And also we have a ship sounding, and also we have the aircraft draft sounding too. So in terms of remote sensing, we want to observe the all-weather condition from the clear air to the precipitation event. So for the clear air, for the measurement of clear air, we set up the 3 Doppler radar, 1 system in the coastal area, and 2 systems in the mountainous valley area. And also, we add the 3 X-band parametric radar, 1 in the coastal area, and 1 in the valley, and the other on top of mountains. And this site here, so TRX UCLM, this site is close to the Mayhill's super site. So we set up there the NASA D3R radar. It's a dual frequency, dual parametric radar system. So in that way, at the single location, we had the triple wavelength measurement with the polarimetric capability. So in addition to that, we want to have observation of a cloud. So we set up the vertically pointing cloud radar at the Mayhill's super site. In that way, we have a sort of observation from clear air, cloud, and precipitation measurement too. So all those remote sensing instrumentation actually has a synchronized scanning strategy. For the radar system in the left-hand side, they actually has a scanning strategy of repeating every 5 minutes with the RHI and PPI and the 90-degree vertical pointing observations. And also, radar system in the right-hand side actually has a 12-minute repeating cycle, but that has a very similar scan as a radar system. They had RHI and PPI, but they had one more system we call the 80-degree scan. So this is in particular we call the window profiling mode. So it has window profiling mode as well as the vertical pointing mode. In that way, we can get the high resolution window information too. So this is a summary of a snow event during the experiment. Experiment lasted from November 2017 to April 2018. So it lasted pretty long. But of course, the weather wasn't incorporating. It was pretty dry. So in terms of Olympic game, they had perfect game. No precipitation, no snow. Every day was okay except for the winter event. But in our side, so we had some precipitation in between games, like between the regular Olympic game and Paralympic game. And also we had some precipitation in late after actually the experiment, after Olympic game. So we have a so-called 8 major snow events. So this shows the snow depths and the prevailing wind in the mountain area as well as the coastal area. And then we had 2 cases, number 2 and number 5. That's we call the GPM. We have the GPM overpass. So in general, by looking at we had a few, maybe 3 or 4 major events here. So we have a decent precipitation here and here. But looking at the period when we had the precipitation is like it's early spring and early winter. So what happened is most of precipitation is mixed. We had in some case it's rain. In the coastal area, it's raining. In the mountain area, it was starting with the rain, and they switched to the snow event. So it was sort of, in terms of precipitation types, it was a perfect experiment, actually. So this is animation of radar reflectivity composite. So without any detailed quality control. So usually I was talking about east snowstorm. So those east snowstorms usually require cold air outbreak. So when you have a high pressure system in the northern part of Korea around here, that will generate the northeasterly flow. And also when the low pressure system is around here, then they bring the easterly flow. So what happened in here, most of a snow system or the precipitation system driven by synoptic system. So you see the passage of a low pressure system from the west to the southwest to the, the eastern part of Korea, and they generate big precipitation over the entire Korean peninsula. And later period when this low pressure system actually passing the South Korea, then they start to bring some easterly flow. So that was the only case we had the easterly flow in this case. So this is a summary of, for the entire experiment. So we try to see the spatial variation of velocity and diameter relationships. We had so many supersites. Try to see what kind of precipitation types or habit we had. So this is there is a small image there, but y-axis for each individual diagram is velocity, and x-axis is diameter. So you see in the coastal area, you have high frequency in the high fall velocity mode. So we call it rain mode. So mostly in the coastal area, we have a lot of event with rain. But if you go to the mountain area, now you start to see the so-called second mode here. So which is a low velocity mode, it's a snow mode. So you see some change of precipitation habit there. In the mountain area, so we have a second mode become more dominant now, like here. So in this small mountain venue area. So with this supersite observation, we classify precipitation type. So this is summary for the entire experiment. And in the coastal area, so we have 1/3 was rain. So the blue one is rain and snow and mixed. So 1/3 was rain. But if you go to the mountain area, now the more snow start to kick up, so over 50 to 70%. And then in mountain venue area, so almost 70 to 90% was snow, and a little bit of rain. So the overall in terms of precipitation types in the mountain area, dominated by the snow and some cases of rain and snow mix. But in coastal area, it's sort of we have a sort of well-balanced precipitation habit type there. And this is again summary of a precipitation habit at the Mayhill's supersite. So this has been done by the multi-angle snow camera. So we identify individual snow flakes and then classify them as whether what types of snow particle there is. So it's either snow crystal or it's graphel or aggregate. Okay. So this is again 1/3 was aggregate in the mountainous area, and also we had the significant amount of graphel, about 16% was graphel. Okay, so we collected the data, and then, of course, we went through the very massive quality control. So for the weighing gauge, so we followed the WMO-SPICE quality control algorithm. So during the experiment, we collected data every 6 seconds, and then after QC, we degrade the time resolution into the 1 minute. And the digitometer, ground-based digitometer, precipitation, and 2DBD, all those are quality controlled based on the fall velocity information. And then we come up with 4 different levels of a product. So it's a raw data types, raw data, no QC, and QC and product. And also, one of our experiments, what we did is before this IcePop 2018, we actually co-located the entire digitometer into the single location. And in that way, we can do the cross-calibration with the rain observation before the experiment. And we had a Doppler radar, so we implemented the radar and algebraic text-based quality control algorithm. In the radar QC, we spent a lot of time. So because we are talking about mountainous areas, so the radar data is really, lousy, So we applied the single and the dual fuzzy logic algorithm, as well as we applied the clutter map 2. And the velocity de-aliasing, we use the 3 techniques: 4-dimensional de-aliasing, unwrapped phase algorithm, and de-aliasing using robust fit. And also we need to calibrate all the instrumentation. So reflectivity, we did a self-consistency between reflectivity and specific differential phase. Also we made intercomparison with different radar, and also we did the geometric calibration, and we also did the monitoring of ground color too. So GDL calibration, we compare with the climatological dropside distribution as well as vertically pointing measurement too. So this is an example for the radar calibration. So this is a calibration constant derived from the self-consistency. You see the calibration bias is pretty constant along this period, and then they suddenly jump. So immediately we don't apply these biases. So we try to look for the second evidence. And then this is coming from the intercomparison between 2 different radar. So again, intercomparison show the same trend. So you see the one calibration constant and goes up again. So again, now we are a little bit confident. And then finally, we went through the monitoring of ground color at a different reflectivity level. So we are pretty making sure there is some sudden change in between 2 periods. So we repeated all this procedure for the entire radar system and then come up with the radar calibration constant. And this is an example of radar QC. First, eliminate non-meteorological echo. This is a radar measurable from the operational S-band dual parametric radar from the Ministry of Environment. So this is before the QC, and this is after QC. And this is for the D3R measurement at the super site. So this is before QC, and this is after QC. And then this is the example for the velocity de-aliasing. Left-hand side is before the velocity de-aliasing. You see the folded velocity everywhere around here and some speckle there. This is cleaned, unfolded velocity information too. So we repeated all this for the entire data set. And then now we are working on the generating product. So we try to develop the precipitation product, 3-dimensional precipitation product, as well as wind information. So for the wind information, we had 2 domains. So one we call the precipitation event domain. So we had about 150 by 150 kilometer domain and 10 kilometer in vertical. So we generate 3-dimensional wind at 1 kilometer in horizontal and 250 meter in vertical resolution. And also we have a so-called LiDAR domain. So this domain applied for the only clear event. So in that way we have more, the LiDAR information kick up more. So in this domain we have about 100 meter by 100 meter domain resolution and 250 meter in vertical direction. So okay, so this is I will show some example how the retrieval different from the NWP reanalysis field. So this is a KMA model reanalysis at the 1.5 kilometer resolution. We matched the resolution in 1 kilometer. So black one is reanalysis from NWP model. They actually add all those observations. So to do the reanalysis. And then I put the 3 pink line arrow. They are the actual observation from the sounding too. So you see some discrepancy between the even reanalysis. The analysis field quite different from the observation. And then this showed the wind retrieval, 3-dimensional wind retrieval at 3.5 kilometers at the same height. So we have 2 ways. So the black one is the original 3-dimensional wind retrieval. And here the beam 45 means we include the beam broadening effect. So now you see the change from left-hand side to the right-hand side. Although you see you start to see the convergence there, wind actually deflected into this direction, more parallel to the coastal line too. So, and then you start to see some convergence line here too. And now I will show some cross-section along this direction. So this is a cross-section from the reanalysis and the actual retrieval. So here you see in the upper layer, you see the westerly flow, and the lower layer, you have easterly flow. So this is sort of a typical flow in this event when you have a northeasterly flow event, and then precipitation generated. So but in the real analysis, this we call the turning layer actually doesn't change. More or less, they are constant layer. But if you look at the actual retrieval, so you see so much change here, all go up and down, going down or up. So you see so much variation in those turning layer. As well as you see those circulation is well shown. So all those structures are really shown much better than the real analysis field. Now this is a comparison with the actual sounding as a function of height. So there is a sounding black, and model real analysis light blue, and then do the blue and the red is actually retrieval. You see how much change, so the model real analysis is so much different from the observation. So, but if you look at the easterly flow and the westerly flow, actually pretty well reproduced by the proper retrieval method. And then the LiDAR domain. So left-hand side is retrieval without any LiDAR information. So it's a little bit lousy image, but there is a contour line that's actually observed the Doppler velocity from LiDAR. And then there is a color scale. Color scale is a radial velocity retrieved through the algorithm. With this left-hand side, without any applying the Doppler LiDAR, and right-hand side with applying Doppler LiDAR information. So I'll see here, this is a retrieved, white one is a retrieved Doppler, zero isotope, but the actual zero isotope is here, black line here. So their wind direction is completely different. So it's more like a southwesterly flow comes in. But in the reality, actually what's happening is a more easterly flow, and then this side is a northeasterly flow. So that's actually corrected, low-level wind actually corrected by the actual observation from LiDAR. And then now we are working on the different product. So this one we call the snow microphysical product. We try to get the snow density information. So here the color actually frequency from the actual data set. So for the individual snowflakes, we calculate the density information and then put into here. So all those millions of snow particle information actually go here. So and then we try to fit. So that will be the black line here, this one. And then for the comparison, we put some literature relationship there. So so our density diameter relationship actually a little bit above. It's more dense compared with the Helmsfield equation, but low density compared with the Holloyd and the Brandeis equation. And then we made some evaluation whether our equation really, our density diameter relation is proper for our environment to compare with the pluvial snow water equivalent. So if we use our equation, it's much better. But if you use Holloyd literature equation, actually they overestimate.
What's that DMPP size?
It's apparent size. And now I will show some example for the cases. So this is the fourth case, 28th of February to 1st of March 2018. So the lower image is a 2D map, rainfall map. So you see the band here. And then we had one radar here, another radar here. So what we did is we had a sort of co-located, aligned RHI observation. So this radar was doing RHI in this direction, and also this radar was doing RHI this direction. So we combine two RHI information, try to see what's happening in along this direction too. So in the coastal line, so you have the topography there. In the coastal line, you see the radar bright band. So again, in this case, in the coastal area, we have rain, and in the mountain area, we have a snow event. And then you will see the two RHI observation along the mountain range. So this is what you see. So in the coastal area, you see clearly the radar bright band there, and then very deep system developing. In the mountain area, it's a relatively lighter precipitation compared with the coastal area. For this case, we have observation from the super site. So it's a reflectivity and Doppler velocity measurement from the vertically pointing X-band radar. And then we overlapped with another observation. This is sounding observation. And also there is a temperature information from the sounding to every 3 hours. So this is a minus 10 degree and minus 20 degree. So as you see here, for the early period, so this we lost the data here. So early period system is pretty deep. They go to up to 8 to 10 kilometers. So it was a pretty deep system. So this shows the sort of typical precipitation system you see in this area. And then the later period, the system becomes very shallow. The level reaches to over 4 or 5 kilometers. So usually they have a very deep system. Whenever the low pressure system passing by, they have a deep system develops. And then later when the easterly flow comes in, then the system becomes weaker and then become narrow. So, but in this case, the wind really didn't turn into the easterly flow. Still, it has a westerly flow in the mountain area. And then this is the D3R measurement. So reflectivity upper panel and the differential reflectivity from KU band radar and the rho HB. So again, you have a big missing data there. But beside that, what you see here, so I will show some discrepancy between this period where the system is deep and when the system is shallow, okay?
So, GyuWon,
yeah.
So essentially, the heavy precipitation is brought by synoptic system, not upslope.
Yeah, but you have to be careful, The reflectivity, only this period reflectivity is high. But here, reflectivity is not that weak, It's a shallow system, but precipitation is pretty heavy. So I will show why you have such a huge reflectivity here. So although reflectivity is higher, in terms of precipitation, it's a little. So this is the same location, reflectivity and GDR measurement. So if you look at the GDR measurement, so early period here, so although we're missing data everywhere, but we have a relatively high GDR, 0.8, 1 dB. But later period, GDR become much smaller. It's a negative value. Okay?
How much that, you said your data quality was performed on that second image there, and I see the light blue on GDR.
Yeah.
Just a load of minus 3 dB ZDR. That's poor data quality there. Is there a reason for that?
But I'm not sure. But the team, the D3R team actually claimed the radar is perfectly calibrated.
Perfect.
Yeah. So they didn't see much, the discrepancy in the even KU and KA band, and also the GDR properly calibrated. So that's how we use that data. So again, I agree. Yeah, you have a lot of negative value there.
Is it the X band or what?
It's a KU band measurement. And then the early period, what you see here, this is we call the microphysical product from the mask. So there is all different line. So this is a precipitation habit, and then the degree of melting and degree of riming. Okay, so you see the blue line here. Basically, in the early period, most of precipitation was aggregate. In the later period, you start see the purple line. That's more like graphel types. So early period, you have lots of aggregate, and also the degree of riming in the black line, that you have a lot of riming in the later period. And also, if you look at the velocity information, so early period here, so you have a lot of big drops with a low velocity, but in the later period, you see the small drop, but the high fall velocity. And then this is a summary statistics for the early period. So it is a shift out for the reflectivity and Doppler velocity for the first period. What you see is the general increase of radar reflectivity. So basically, it says growth of snow. And then the early period in the upper layer, when the reflectivity growth, velocity also increases. But velocity doesn't increase that much. The growth rate is, the velocity increase rate is very gentle. So basically what it means is mostly the depositional growth. And then when it comes down, the velocity doesn't change. Reflectivity gently increases. So the velocity doesn't increase. That means it's basically low density particle. It's aggregate. So this is the snow image at the ground we measure from the mask. So you see a lot of aggregate there. And this is the second period. So you see the depth of storm. So compared with the upper one, so storm is just 3 kilometer depth, but you see how the reflectivity increases. There is a dramatic increase of mass with a different height. And also you see the velocity increase. So the velocity is increased so much. Basically that indicates the high density particle were generated. So you see a lot of graphite and heavily limed particle for the second period. I'm running out of time. Yeah. So we are working on snow QP in 3 different ways. First one is a reflective-based QP. So we use the hybrid surface rainfall map. So this is terrain following adaptive method. So we also do the adjustment with the weighing gauge. And we are working on the dual wavelength QP, but we didn't have a much data set to do the dual wavelength QP. So this is more like research mode. We cannot provide operational product for that. And we are working on the polarimetric QPE. So one of the advantage of doing polarimetric QPE is we try to pick up where is the peak value of KDP and GDR. So in the layer of dendritic growth, it will be typically minus 15 to minus 20 degree layer. And then there we estimate snowfall rate and then convert into the ice water content. And then again, the snow estimation was done upper layer. Then we should let it grow at the below layer, assuming with a temperature profile and moisture profile. So this is an example of snow radar reflectivity-based QPE product, snow QPE product. And then this is the verification. So blue one is without adjustment, and the red one is with adjustment. And we generate a precipitation product for 8 cases. So in that we put this whole data set into the deposit, and then people can use it now. And one of my postdocs was working with the precipitation system, how they interact with the topography. So this is a small domain in those Pyeongchang area. You see in the early period when you have a high reflectivity value, and also you see the high reflectivity value here. So there are 2 locations you start to see the reflectivity, and then let's go. And here, like here, reflectivity, high value and high value. So westerly flow in this case. And then you start to see the convective line off the coast over the ocean. So like here now. And then suddenly they move to the coastal area. Okay? So this is a homology diagram over this domain. So average for this domain in this direction. Okay? So it's southwest and northeast. So reflectivity and wind information. So you see the topography here, coastline is here. So in the early period, you have reflectivity here in the western side. It's linked with the southwesterly and southerly flow, and then the southeasterly flow. They actually merge. So in this case, what happens is you have a westerly flow. They carry over a lot of small light precipitation particle to the eastern side, and then they make a seed feed effect. And then later effect when wind become easterly flow. And what happens is the convection start to develop over the ocean. But during this period, I'm not showing here, but what happened is along this line, there is a very strong northerly flow. It's like a low-level jet actually developing along this line. So that prevents this term actually coming in. And then when wind start to deviate a little bit further to the northeasterly flow, then the low-level jet disappear, and then you start to see that this convective line comes in. And then we are working on the prediction of precipitation types. We are using spectral bin classifier SBC model developed by Jacob and Lichkov, 2019. So basically, this is a bin microphysics scheme developed by them. And then this can be initiated with the retrieved snow size distribution at the upper layer in the like -20 and -15 degree layer. And then it has a process of melting and sublimation, evaporation, condensation, and deep-freezing processes. And it also interacts with the environment. So this is one case in the 4th of March 2018. So measurement with the vertical pointing X-band radar over the supersite. So you see the reflectivity image. You see the melting layer here. So melting layer slowly comes down. And then around 15 UTC, they disappear. So basically, early period, we had the rain, and then they switch to the snow. So it's a sort of a perfect case. We see the test our prediction, SBC prediction skill. So this is observation from the 12 to the 15 UTC with the gyrometer. So early period, the high velocity mode you've seen. So it's mostly it's rain. And then you slowly start to see some mixture of precipitation. And then they start to disappear. Rain slowly start to disappear and switch to the snow particles. And then this is observation from the mask multi-angle snow camera. You see the raindrop there. And then partially melted. And then aggregate. So later period, around 15 UTC, everything switched to the snow. So this is the output prediction result from the SBC model. So left-hand side is the temperature, vertical profile of temperature and vapor temperature. And right-hand side is it's melted liquid water fraction as a function of height and melted diameter. So blue one basically means it's ice. It's snow. And the red one is basically the raindrops, liquid phase. So early period, around 12 UTC, so everything was rain. And you slowly start to see the snow actually kicking up. And then this doesn't actually pushing further. So because you need to see the leaf freezing of a snow particle. That doesn't suddenly occur. And then certain time when the temperature actually pushes further to the cold, then start to refreeze. So this is a result for the entire experiment. We had about 110 sounding observation. And then we run all those sounding with the SBC model. And then we made some comparison with existing operational product, like there is some algorithm that use thickness and improve the Mastrobe method and the TW method. And this is developed from the USA. So they're using the wet bulb temperature as well as lap slate at the lower layer. So here, the x-axis is actually true precipitation type. And then the color is predicted precipitation types. So like a snow, so if you have the white big fraction of red, then the performance is really good. But the opposite here, blue one should be big, okay? So in general, what you see here, so in general performance, this will perform best, okay? So the SBC model properly introduced, but it has some issue with that here too. It doesn't properly, predict, the mixed precipitation types. This is a collaboration with the Swiss team, Alexis Bond team. So they had the cloud radar in the supersite. So this is reflectivity and Doppler velocity from the W-band cloud radar measurement. And you see a lot of updraft here in the warm color. And then with the dual pole parameter, they classified the precipitation types as a function of height. And the early period is mostly ice crystal, and later period you see the aggregate. But in the period between 0.6 to 0.8 UTC, where the heavy precipitation were there, so they start to have a lot of rimed particles. So basically, this period you have lots of rimed aggregate of rimed particles. So this is RHI image over the cloud radar. So you see the two layers of growth. So one is here, the other growth layer here. So and then if you look at the north in the northern direction, RHI in the northern direction, and then you see the very strong wind here. So they claim that this is one conveyor belt. And then if you look at the average of reflectivity and GDL spectral width from the RHI scanning data, then that's what you see here. So reflectivity grow in general, and then the growth rate become a little bit weaker here. But if you look at the GDL value, so the GDL suddenly increases and then start to decrease. So basically from here to here, reflectivity increases, GDL increases. It's a depositional growth. And then the GDL start to decrease, but still reflectivity increases. But if you look at that period, you have a very high value of spectral width, basically indication of turbulence. So this, the area actually is a turbulence-driven aggregation layer. Okay, so we are working on also some impact on the snow retrieval from the satellite. So the team from the FSU, they actually classified the precipitation system into three. So one is a deep system. So deep system, they certainly sure they can get the snow information from satellite. And then the shallow is in between. So that top is about 1.5 to 4 kilometers. So sometimes they do and sometimes they doesn't, okay? And then the very shallow layer, like here, very shallow, but this doesn't, the satellite never see these types of snow event. So they classify into like a very shallow, and the deep system. And try to see what's happening in the snow water equivalent and liquid water path. So mostly in this area, the very shallow system was over 60%. So although during this period we have so much synaptically driven system, but again still in terms of precipitation type was dominated by the very shallow system. It's up to the lower than 1.5 kilometer. And then this figure becomes very interesting. This is the snowfall rate, and this is liquid water pass for the three types of system. So here in the deep system here, so they generally they have a heavy precipitation, the heavy snow water equivalent. But generally they are pretty dry sometimes. But if you look at the very shallow system here, yellow one, their general snow water equivalent is very low, but there are a lot of liquid water pass. Basically what it says, you have very shallow system, there is a lot of liquid water. And then some cases like deep system, they produce some significant snow amount, but what happens is they are pretty dry. So mostly in terms of microphysics, this shallow system driven by the rhyming process. And this heavy precipitation, while the deep system has more driven by the aggregation processes. Okay, so this is a sort of a summary in terms of microphysics. So again, we had the supersite along the flow, from the coast to the mountain top and the valley area, okay? And then this is a measurement from the micro rain radar, and reflectivity, and Doppler velocity, and spectral width. So let's look at the reflectivity. So reflectivity shows more like upper layer gentle growth there, and then they remains constant, okay? They don't see much generation or new development at the lower layer. But if you come to the mountain area, look at the reflectivity value. Reflectivity value become higher than coastal area. So that persists to the valley area too. So what happens is, in general, in the ocean area, the reflectivity is small. But if you come to the mountain area, and on top of mountain valley area, the reflectivity becomes stronger and stronger. And if you look at the velocity information, velocity doesn't change with height. Basically, there is no change of density of snow particle along the height. But if you come to this area, mountain top and the valley area, what you see, you start to see second peak here. So it's a high velocity mode. So it has higher velocity or similar reflectivity, but much higher fall velocity. Basically, again, this is rimed particle and graphite particles. So basically, this all mountain area is driven by when the easterly flow comes in, it generates updraft that produce a lot of supercooled water that make a lot of riming and the graphite particles. So that's shown by here. So you don't see much change here in the spectral width, but if you look at this layer, there is some kink in this direction. This is the layer you have a turning layer. Below it's a easterly flow. Upper layer is a westerly flow. So there is where you have a strong directional wind shear there. Okay, so for the easterly flow, this is in terms of windward side, in the coastal area, we have lots of big particle. But if you come to the mountain area, the big particle disappear, a lot of small particle appear, and the high fall velocity. And then if you get the climatology of a microphysical parameter in terms of N0 prime and the DM prime, then this is the leeward side minus windward side. Basically, positive means the leeward side has high number concentration, high frequency, and windward side high frequency. So what happens is here, when easterly flow comes in the east side, coastal area, you have lots of big drop there. But if you come to the valley area, mountain area, you have more smaller drops and high fall velocity drops. I think that's my last slide. So this is summary. So we are working on applying the cleaning data set. In that way, everybody can use it. And we also generating product. So that includes precipitation, habit, snow size distribution, fall velocity, and density information. We are working on radar snowfall rate. And we're also working on the high resolution 3D wind and precipitation product and various microphysical product. So we are working on the precipitation mechanism and the microphysical characteristics. So the experiment actually officially ended. And the KMA generals provide further funding for the phase 2. So phase 2 is basically we have plenty of data. We want to do the real science instead of quality control. Okay. So this is sort of overarching goal for the phase 2. So we wanna work on the analysis and prediction of precipitation amount and types. So that includes quantification of snow amount. So in terms of radar and GPM and analysis too. And also we are working on the classification of cold precipitation type at the surface as well as above. And also we are working on the prediction and outcasting of winter precipitation. So we haven't done much on the data simulation side. So we will work on the data simulation as well as we have such a wonderful data set in terms of microphysics. So we want to look at the bulk microphysics in NWP models, how this riming and the melting process is handled in the bulk microphysics scheme. So in that way, we can really improve or watch the behavior of different microphysical permutation scheme in terms of riming as well as the melting processes. I think that's all. Thank you.
Any questions? I'm sure there are questions.
I want to say something. GyuWon, you had a time period there where you had heavy snow was out over the heavy precipitation was out over the water. And I was curious why. And you said at that same time you mentioned about there was a low-level jet, I think. And I was wondering why you thought there was that heavy band of rain along the coast. Yeah, that's it.
This one, yeah.
Yeah.
This one, yeah.
Yeah, well, the whole thing.
Yeah.
Now, is there lifting over the jet, or is the jet lifting? What's going on?
So in this period, we have a strong jet along the barrier. So there was the eastern part of a mountain range. So the strong jet bring in a lot of cold air from the north. So that sort of a blocking flow comes in from the coast, from the ocean. So you have a very cold air coming from the nose, and you have a easterly flow.
It was
warm air.
riding up over it.
Yeah, blocking
Okay,
and then
that's
go
what I
over
was-
like this. Yeah.
Yeah, okay, that's pretty interesting.
So the velocity at around 500, 800 meters was about 10 to 15 meters per second.
More questions?
Did you do comparing the snow gauge measurements? Since there are so many snow gauges, the DBZ measurements, how they, can you summarize that result? Or?
Yeah, well, but we don't have intensive comparison, but this is one example what we are doing. So this is the product we already generated. So this is original accuracy of blue one is accuracy of original product, and the red one is more like adjusted product.
What are you adjusting?
It's a weighing gauge, and then do the cross validation. So in this area, we didn't have many weighing gauge. So it's about 20 weighing gauge in this location. We use that as adjusting the radar precipitation.
That's for a rain situation?
Snow, yeah.
Anyone else?
I have a question about the fraction of melting, like you show in the that one, and what can you explain why there is a sharp gradient when it goes down? Like
It's basically refreezing process. So the let's say temperature goes down, so then it becomes -2 and -3. They are not immediately freeze. So they need to have a certain critical point to refreeze. So that's what you see here. So you certain, the line there. And when the temperature becomes much lower, then start to refreeze.
And when you want to improve the microphysics parameterizations, how do you use the observation to? Will that be a problem?
We are working on, yeah. So it's a more like an easy problem. That will be a melting issue. And then so we try to. It's an idea. We try to develop some lookup table with this model run for many cases, and then use that lookup table to parameterize the bulk scheme.
So a lot of the radar data, I think you have this experience of attenuation. How you get it correct for all that attenuation?
You need to help me. So there might be issue with KU and KA. So, but X-band should be all right.
Well, in the rain.
Rain. But we didn't have much, the rain was relatively weak, Yeah. Only problem is the melting layer.
So GyuWon, you have a lot of data here, a lot of instrumentation, and you must have quite a few people working on the quality control. How many?
All my students.
Dozens?
Steps. Nobody really wanted to do the QC. So that's what we have to do. Well, we nearly complete now. So when last December when we did the workshop, ISPA workshop, so we nearly completed about 80% of QC. So now it's almost 100% complete. So we need to reproduce our product with the QC the data set. Yeah.
Go to the last diagram.
This one? On microphysics or?
No, the one you show. Let's see. At slide 46.
46?
47. I think.
47, okay. How come on.
Well, you have a slide to show, to illustrate liquid water content.
Yeah, okay. I'll show. It's frozen.
Oh, I'll ask you later.
Yeah.
Seems like a computer.
So the x-axis is liquid water pass and y-axis is snow water equivalent.
Correct.
Yeah.
I'll ask you later.
Up. Oh.
Well, it looks like the computer decided we're out of time. But there's still time for one or two more questions.
Yeah, this one. Yeah.
So you said the yellow and the red color. So they seems like on the right hand side around 400 to 600.
Yeah, there are some, yeah.
They're about the same, but just the snowfall rate is different, right?
Very low. And it has a lot of snow water, liquid water pass. So this is more like a deep system, but it has a different microphysics compared with this one. So it's a quite dry environment, but this is not.
That's a different?
Yeah, it's different, yeah.
Did you have a radiometer to get the liquid water path? How did you get
So this is coming from the what you call cloud radar, pointing vertically. So we also had the radiometer too, scanning radiometer from LPG.
From there also can get the liquid water path.
Yeah.
Okay, well, let's thank Professor Lee again.
Thank you.